What's going on, everybody? Got another video here for you in business calculus. This is graphing using going all the way to the second derivative, finding concavity and inflection points. This video goes with the previous one, graphing using the first derivative. So you can kind of put these two sections together and get a nice little graph. Seems like the business calculus textbook split this up into two sections. It's normally taught in one section in a calculus book. But let's go ahead and do it like this, like they do it in business calculus. So it says second derivative test for determining intervals of concavity. So we're going to determine where the function is concave up and concave down. So it says find all values of x for which f double prime is 0 or is not continuous and mark them on a number line. Choose a test number c from each interval a, b, determine in step 1 and evaluate f double prime of c. Then if the f double prime of c is positive, the graph is concave upward on the interval, and if f double prime of c is negative, the graph is concave downward on the interval. So this is going to pretty much be done like when you were determining where the function was increasing and decreasing. We're just doing it with the second derivative, and that gives us the concavity of a function. So let's get started with some examples. So it says determine intervals of concavity for the function. So what we want to do here is we want to find the second derivative. So we got f prime of x is 12x to the fifth minus 20x to the fourth plus 7. And then f double prime of x is, what is that, 60x to the fourth minus, what is that? Oh, I'm sorry. That's 20x cubed. So that's going to be 60x squared. So there's your second derivative. All right, so now let's set this thing equal to 0. So we get 60x to the fourth minus 60x squared equals 0. So we factor out a 60x squared, and we're left with x squared minus 1 equals 0. So we get 60x squared equals 0, or x squared minus 1 equals 0. So here we get x equals 0. Here we get x squared equals 1. So x is equal to plus or minus 1, square root property. Now, what does this say to do? It says to plot these numbers on a number line. So we got -1, 0, and 1. And that's going to break this up into 4 intervals. And we need to choose a number from each interval. So I'll do x equal -2, x equal -1/2, x equal 1/2, and x equal 2. Now, it doesn't matter what numbers you choose. You just have to make sure you choose a number from each interval. And then what we want to do is we want to evaluate the second derivative at each one of these numbers that we chose. Now, just like if you watched the previous video, graphing with the first derivative, and if you haven't, you need to go watch it because you need to know that before you get to this. And also, if you go back and watch the first video, hit the like button on it and the like button on this one, and subscribe if you haven't subscribed yet. But anyway, so what we've got to do is we're going to take this -2 and we got to put it back into the second derivative. But look at this. Wouldn't you agree that this right here, this function here, is the same as this one right here? This is just factored. Okay. So what we can do is we can plug each of these numbers into the factored part because it's easier to determine if it's positive or negative. So look at this first part here. We've got this times this. So if we plug the -2 in, well, actually it doesn't matter what we plug into this 60x squared, it's always going to be positive because it's squared here. So that's a positive. And then if we plug the negative 2 in, that's going to be 4 minus 1. That's positive. So we have a positive times a positive, which that's positive. So that is concave up. And then we have f double prime of negative 1/2. Well, that's positive out here. And then we would have what? 1/4 minus 1 is negative. So we have a negative times a positive is negative. And so that's concave down. And then we have f double prime of 1/2. That's positive. That would be negative in here. So a positive times a negative is negative. And so that's concave down. And then we have f double prime of 2. That would be positive here, positive here. Positive times a positive is positive. So that's concave upward. So here you go. We've got concave downward from -1 to 0 and 0 to 1, and then concave upward from -infinity to -1 and 1 to infinity. That would be, see if I can get this, that would be a 1 right there. And so this is the intervals of concavity. This is where it's concave up and concave down. Now, look, if it didn't make a whole lot of sense to you when I was determining positive, negative for the second derivative by doing this, if you don't understand that, then just take each number, plug it into the function, and see what number you get. Plug it into your calculator and see if it's positive or negative. We don't care about what the exact number is. The only thing we care about is it positive or is it negative. That's it. Okay. All right, so that's determining concavity. We'll do some more problems. The directions don't say find the concavity, find the concave up, concave down, but we have to do that in order to work some of the other problems. So we'll get more practice with that. All right, so inflection points. It says compute f double prime and determine all numbers in the domain of f where f double prime is 0 or f double prime is not continuous. For each number c found in step 1, determine the sign of f double prime to the left and right of c. If f double prime is positive on one side and negative on the other, that should be other side, then cf of c is an inflection point. And then also you can look at it, it's not just f double prime is positive on one side and negative on the other. It could be negative on one side, positive on the other. So it could be positive negative or negative positive. Basically what it is whenever you find that point C, the point C's like this, like we found here, if it changes concavity, there's an inflection point there. But this number has to be in the domain of the function, or it wouldn't be a point there because the function would be undefined there. But as long as it's so notice what it says: compute f double prime and determine all numbers in the domain of f. Okay, so the function has to be defined there in order for there to be an inflection point. So let's work an example. It's probably easier for you to see. So we got 2 problems here to work to find inflection points. So find all inflection points. So we've got to find f double prime. So that's going to be 15x to the 4th minus 20x cubed. And then we have f double prime is equal to, what is that, 60x cubed minus 60x squared. I said 60 and wrote 20. All right, so now we've got 60x cubed minus 60x squared equals 0. So we factor out a 60x squared, and we're left with x minus 1. And so we got 60x squared equals 0, or x minus 1 equals 0. So x equals 0, or x equals 1. All right, so plot the numbers on the number line, and hopefully you can see we're doing exactly what we did in the last problem. We're finding the concavity. So let's pick a number from each interval. All right, and then we have to evaluate the second derivative at each one of these values we chose. And once again, it does not matter what x values you pick, as long as you pick an x value from each region. All right, so we've got f double prime of -1, and once again you plug it back into the second derivative, or we can go ahead down here and plug it into the one that's factored. It's just easier to determine if it's positive or negative. So this number out here is going to always be positive because it's squared. So that's a positive. We're plugging in -1. -1 minus 1 is negative. Negative times a positive is negative. And so this is concave downward. And then if we plug in the 1/2, that's positive out here. 1/2 minus 1 is negative. Positive times the negative is negative. So f double prime of 1/2 is negative. So that's concave down. And then we have f of 2. That would be positive out here. 2 minus 1 is positive. Positive times a positive is positive. All right. So it doesn't ask for this, but let's just write concave downward. They're not asking for concavity, but we're going to do it anyway. So that's -infinity to 0 and 0 to 1. And concave upward from 1 to infinity. That's the concavity. They didn't ask for it. They just want the inflection points. So what are the inflection points? Well, you can see right here at 1, that's the only place that it changes concavity. See, it doesn't change concavity at 0. It just changes at 1. So our inflection point is the point 1. Now we're looking for a point. So we've got the x value, which is 1. So what's the y value? Well, remember, to find the y value, you plug it back into the original function. So that's 3 times 1 to the 5th minus 5 times 1 to the 4th minus 1. And that is going to give us, is that -3? 3 minus 5 is -2 minus 1 is -3. And so here's your inflection point. That's what we're wanting you to find. All right. Not bad. Pretty easy. All right. Let's look at problem 2. Find the inflection points. So I've got f prime of x is 1/3 x to the -2/3. F double prime of x is -2/9 x to the -5/3. So this is actually equal to f double prime of x equals -2 over 9x to the 5/3. Remember, this is over 1. If I move it down to the denominator, it changes the sign of the exponent. All right, so remember, if you have -2 over 9x to the 5/3 and you set that equal to 0, remember, a fraction is 0 when the numerator is 0, and we know that's 2 does not equal 0. So this fraction will never be 0. But at x equals 0, f double prime is undefined. It's not continuous. You see that? Now, let's see. if we plot x equals 0 on the number line, now let me ask you this, can we use 0? Okay, the second derivative is undefined at 0, but are we able to use it? Because remember what it said up here. Where is it? Yeah, compute f double prime of x and determine all numbers in the domain of f where f double prime is 0 or is not continuous. So let's go here. It's undefined at 0. F double prime is undefined at 0. Is 0 in the domain of this function? Is it okay if we take 0 and raise it to the 1/3 power? Sure it is. Okay. So let's do f. Oh, I'm sorry. Let's choose a number. X equal -1, x equal 1. Okay. All right, so f double prime of -1. So if we plug the -1 in, well, what is that going to be? That's going to be -1 down here. Okay, or you can plug it in here, it doesn't matter. But the cube root of I'm going to show you how to get that. It's -1 to the 5/3 is -1, but let's look at it. -1 to the 5/3. I'll show you how to calculate that. You can punch it in your calculator, but this is what it is. It's the cube root of -1 to the 5th, which is the cube root of -1 is -1 raised to the 5th power is -1. So that's 2 over -9 is -2/9, and then the negative out here is going to make it positive, and so that's concave up. And then f double prime of 1, well, that's +1, so that's 2/9 with the negative in front. That's less than 0, so that's concave down. And like I said, you can do that in your head really quick, or you can waste your time and spend some time punching it into the calculator. Well, I don't guess it's wasting your time if you get the right answer, but you ought to be able to do that real quick in your head. So once again, it doesn't ask for concavity, but let's go ahead and put it down. So it's concave downward from 0 to infinity, and concave upward from -infinity to 0. So that's the concavity. They didn't ask for it, but we like to do extra, so we write it down. And so now we have an inflection point. The inflection point, it changes concavity at 0. And so f of 0 is 0 to the 1/3, which is 0. I take the 0, plug it back into the original function. So there's my inflection point, is the point 0, 0. All right, so we've learned how to find concavity. We learned how to find the inflection points. So let's put all of that together with what we learned in the previous video on the first derivative and graph some of these things. I think we got 2 graphs to do. You need to make sure you watch them. All right, so basically what we're going to do, we're going to get our critical numbers. We're going to find where it's increasing, decreasing. We're going to find relative max and min. We're going to find concavity, where it's concave up, concave down, and any inflection points. All right, so let's start. So the first part that we're doing, critical numbers, increasing, decreasing, relative max, min, that's the previous video. Like I said, if you haven't watched it, you need to go watch that before you come in and watch this. All right, so we've got f prime of x is equal to 4x cubed minus 12x squared. All right, so we've got 4x cubed minus 12x squared equals 0. So we're going to factor out a 4x squared, and that's going to leave us with x minus 3 equals 0. So 4x squared equals 0, or x minus 3 equals 0. So that's going to be x equal 0 or x equal 3. So we've got 0, 3. So these are our critical numbers, and we're going to find where it's increasing and decreasing now. So we're going to use x equal -1, x equal 1, and x equal 4. And we're going to put each of these into the first derivative. So you can plug it into here, but I think it's easier to plug it into the one that's factored already. So f prime of -1, that's going to be positive out here. -1 minus 3 is negative. Positive times a negative is negative. So that's decreasing. And then we've got f prime of 1. That's positive out here. 1 minus 3 is negative. Negative times a positive is negative. So that's decreasing. And then we've got f prime of 4. Positive. 4 minus 3 is positive. Positive times a positive is positive. So that's increasing. So we've got decreasing from -infinity to 0 and 0 to 3. And we've got increasing. We've got increasing from 3 to infinity. And, you know, what I like to do is I like to come over here and kind of circle this. I know that's not the final answer, but I like to circle it because that's what we got to use that for our graph. It just makes it easier for me to go back and find it. All right, so now we have relative max, relative min. So we've got relative minimum. Well, if you remember from the first video, okay, like I said, you got to go watch the first video. We have a relative minimum right here at x equal 3. And then how do we find the point, the relative minimum? We need the y coordinate, so we take the 3, plug it back into the original. I'm gonna have to get my calculator out for this. So that's going to be 3 to the 4th minus 4 times 3 to the 3rd plus 10. And that gives me -17. So 3 -17, we have a relative minimum. And then we have a relative maximum. And you can see here, see how this is your relative min? This isn't increasing. It's not going from increasing to decreasing. So relative maximum would be none. And so I like to circle this. That's my relative minimum. I'm going to use that. All right, so this was basically the first video, graphing with the first derivative. Now let's find concavity. So for that, I need the second derivative. Well, here's my first derivative. So the second derivative would be 12x squared minus 24x. And so 12x squared minus 24x equals 0. So 12x times x minus 2 equals 0. So that's going to give me 12x equals 0, or x minus 2 equals 0. So I get x equals 0 or x equal 2. So we need to plot those on the number line. So I've got 0, 2. And so I've got x equal -1, x equal 1, and x equal 3. Okay. All right, so let's see what we've got here. So I've got f double prime of -1. So that's a negative here and a negative here, right? Yep, negative and negative. So a negative times a negative is positive, so that's concave up. F double prime of 1, that's a positive, times a negative is negative, so that's concave down. And f double prime of 3, positive, positive, so that's positive, that would be concave up. So concave downward from 0 to 2, concave upward from negative infinity to 0 and 2 to infinity. All right, so now we can find our inflection points. So we've got an inflection point at 0 and at 2, right? It changes concavity at 0 and it changes concavity at 2. So we've got f of 0 and f of 2 that we need to find. So we can see if we plug 0 back into this original function, we're going to get 10 as an answer. So that would be 0, 10. And then if we plug the 2 in, oh, what is that going to be? Is that going to be 16 minus 32 plus 10 is negative 6. All right. All right, so here's the concavity. And here's your inflection points. And now we are ready to graph this thing. So let's see what this is going to look like. See if I can draw that a little straighter. All right, so let's plot our points here. What points do we have? 3, negative 17. So let's just do 1, 2, 3. Negative 17, we'll call that about right there. And 2, negative 6, that's probably going to be about right in there, I would say. Okay, we'll just say that's negative 6. We'll say that's negative 17. Numbers are pretty big. That's the point 2, negative 6. And then we got 0, 10. So we'll call that about, I'd say about right in there. 0, 10. Well, you can call it that, or we can say that's 10. All right. All right, so let's see what this thing's doing. Let's look at increasing and decreasing. So from negative infinity to 0 and 0 to 3, it's decreasing. So that means from negative infinity out here, it's decreasing all the way to 3. Okay, but look at this. It's going down, but notice from negative infinity to 0. Oh, wait a minute, let me say something. Yeah, from negative infinity to 0, it's concave up. So it's decreasing, but it's concave upward. And then once it gets here at 0, from 0 to 2, it changes to concave downward. So let's see if I can kind of make that look decent, half decent. So it looks like that. And then once it gets to 2 to infinity, it's concave upward. So it's coming down like this. And when it gets here, see at 3, at x equal 3, where is it? It starts increasing again. Well, hard to draw these things on this screen. It's kind of slippery, but that's what your graph is going to look like, something like that. Okay, see, it's concave up, changes to concave down, and then it changes to concave up again, and it's decreasing all the way to 3. All right, that's your graph. All right, let's look at another one. All right, same thing. So we've got f prime of x is equal to 3 times x minus 2 squared times, so I don't need to write this, but I'm going to write it anyway so you can see it. Remember, when you're taking the derivative using the chain rule, the 3 comes down, subtract 1 from the exponent, and then it's times the derivative of what's inside the parentheses. So what's the derivative of x minus 2? It's 1. And then 1 times 3 is 3. Okay, so let's set this equal to 0. 3 times x minus 2 squared equals 0. Well, this is just 0 when x minus 2 equals 0, so we get x equal 2. And so let's plot that on the number line. So I've got a 2 there. So I'm going to choose x equal 1, x equal 3. So we need to plug each of these in. So I've got f prime of 1. So and I can plug it into this one. I mean, it's like it's already factored. So x minus, well, look, we don't even have to plug it in, do we? We see that squared. That's the 3 is positive. This term here is going to always be positive no matter what. So we can see that both of them are positive. So this thing is increasing. So decreasing, decreasing, none. It's not decreasing anywhere. And then increasing, it's increasing from negative infinity to 2 and 2 to infinity. It's increasing from negative infinity to positive infinity. That's all the function's doing, is increasing. All right, so now let's find the second derivative. So that's the derivative of this. The 2 comes down, so that's going to be 6 times x minus 2. Subtract 1 from the exponent, so that's to the first power, times the derivative of what's inside the parentheses. The derivative of x minus 2 is 1. 1 times 6 is 6. And so the second derivative, 6 times x minus 2 equals 0. Well, that's 0 when x minus 2 is 0, so x equal 2. And so we've got a 2 here, and I can choose x equal 1, x equal 3. So f double prime of 1. So if I plug the 1 into here, that's a negative times a positive is negative. That's concave down. And f double prime of 3, that's a positive times a positive is positive. So that's concave upward. And, oh, and one thing I forgot to do, let's write it down. Relative minimum is none, and relative maximum is none. Because see, it's not changing increasing, decreasing, or decreasing, increasing. It's just strictly increasing. So there's no relative max or min. So those would be none. And then let's circle this. Remember I told you I circle things that I have to use to graph. And so this thing is concave downward from negative infinity to 2, and concave upward from 2 to infinity. Let's box that in because we're going to use it. And then we have an inflection point. Just got 1 on this one because it changes concavity at 2. So we have an inflection point at 2, and then I do f of 2. So if I plug 2 into here, 2 minus 2 is 0. 0 cubed is 0. So my inflection point is at 2, 0. So let's graph this thing. So really the only point I have to plot is that one right there. It's the point 2, 0. All right, so, I mean, if we wanted to, we could get another point. We could evaluate this function at 0 and get 0 minus 2 cubed is 8. I'm sorry. It is negative 8. That would give us the point 0, negative 8, wouldn't it? All right, so let's just come down here and put that negative 8. Let's put point 0, negative 8. And that'll give us 2 points to do. Now, what is this thing doing? Well, the whole time from negative infinity to positive infinity, it's increasing. Okay, so look at that. It's coming here and it's increasing the whole time. But let's look. From negative infinity to 2, it's concave downward. So this thing is going to come in here like this. Okay, it's concave downward. And then once it gets to 2, from 2 to infinity, it's concave upward. So it's going to do this. So it's going to look something like that. I'll exaggerate it more. It's going to do like that, something like that right there. Okay. It's hard to sketch these graphs when your marks aren't evenly spaced and it's not to scale, but you get the idea of what it's going to do. Oh, and I forgot to circle my inflection point because I told you I circle or box it in when I have to use it. All right, so we're almost done. We don't have too much left, so just stick around to the end. All right, the second derivative test. So if you remember, in the first derivative, in the first video, graphing using first derivative, and if you hadn't watched it, like I said, go watch it, hit the like button on it. We determine relative max and min using the first derivative. And, we did that up here in this problem where it had there it is. See, we looked at increasing and decreasing, and where it changed, you had a relative min. And now look, if you have a number line, you have something like this, and it increase, decrease, increase, this would be a relative maximum, this would be a relative minimum. That's using the first derivative. But you can also determine this using the second derivative test. And the way you would do that, I don't ever use the second derivative test when I'm graphing and doing relative max and min, because you find out where the graph is increasing and decreasing, and you have it right there. You don't really need to use the second derivative test, but it's in here, so I'm going to show you in case your teacher makes you do it. Suppose f double prime exists on an open interval containing x equals c, and that f prime of c is equal to 0. If f double prime of c is positive, then f has a relative minimum at c, and if f double prime is negative, then f has a relative maximum at c. And if f double prime of c equals 0 or does not exist, then the test is inconclusive. You could have a relative max or a relative min or neither. You don't know. And that's where you would go back and use the first derivative test. But like I said, I used the first derivative test anyway. And that's like what we did in the previous video. All right, so it says find the critical points of this function here and use the second derivative test to classify each critical point as a relative minimum, relative maximum, or minimum. So we've got f of x equals 2x cubed plus 3x squared minus 12x minus 7. So I do f prime of x is equal to 6x squared plus 6x minus 12. And so I got 6x squared plus 12x plus 6x minus 12 equals 0. So I'll factor out a 6. Why did I put a plus sign twice? Plus x minus 2 equals 0. So x plus 2 times x minus 1 equals 0. So x equal negative 2 or x equal 1. All right, so that's what it said to do. Suppose f double prime exists on an open interval containing x equals c, and that f prime of c is 0. So that's where we get our numbers from the first derivative. And so now, normally what you would do, and you're going to want to find out where it's increasing and decreasing anyway. You're going to want to figure that out anyway, because you want to know where the graph is increasing and decreasing. But here we don't have to graph. They don't ask where it's increasing or decreasing. They're just asking for relative maximum and min. So see, normally what we do if we were graphing, we would do all this, pick x equal negative 3, x equal 0, x equal 2 and see where it's positive and negative. Okay, and then where it changes, increasing, decreasing, or decreasing to increasing, that's going to determine your relative max and min. But with this second derivative test, you don't have to do that. All we have to do is find the second derivative, which is 12x plus 6. So we just take the derivative of that. And so if we do f double prime of negative 2, that's going to be what? 12 times negative 2 plus 6. I can see that's negative 24 plus 6. That's negative. That's less than 0. And so what does it say? If the second derivative is less than 0, then you have a relative maximum there. So here we have a relative maximum at negative 2, and then we do what? F of negative 2. So you would plug negative 2 into here. And what would that give you as an answer? That equals 13. So you got a relative maximum at negative 2, 13. And then we test the 1. So f double prime of 1. Let's see. Now f double prime of 1 is equal to 12 times 1 plus 6, which that's positive. So that means we have a relative minimum at 1. And we need the y coordinate, so we take the 1 and we plug it back into the original. And that is equal to negative 14. And so there's your relative max and min. All right. And so that's finding relative maximum and minimum using the second derivative test. Like I said, I don't hardly ever use that. I do it with the first derivative because you got to find increasing and decreasing anyway. All right, so let's look at this problem. We got us, of course, business calculus class. You've got to end with a word problem, don't you? All right, it says an efficiency study of the morning shift at a factory indicates that an average worker who starts at 8 a.m. will have produced this many units T hours later. At what time during the morning is the worker performing most efficiently? Okay, so we've got Q of T is equal to negative 3t cubed plus 9t squared plus 12t. All right, so he goes from 8 a.m. and he starts at 8 a.m. and this is during the morning shift. Okay, so 8 a.m. is going to represent, let me write 8 a.m. is going to represent t equals 0. So we're going from t equals 0 to t equals 4. Now where did 4 come in? Because they didn't say anything about 4 in the word problem. Well, it said the morning shift. So we're going to assume that the morning shift is from 8 to 12. So this would be to 12 p.m., which would be 4 hours later. Okay. All right. So we want to know at what time during the morning is the worker performing most efficiently. So we want to know, when is his rate of work the highest? When is his rate of work the highest? So we don't have his rate of work, do we? They don't give us a function for his rate of work. So let's think about this. Well, this function tells us how many units he produces. That's from 8 to 12, he produced this many units. Oh, well, wait a minute. If we take the derivative, that tells us the rate at which he produces them, right? So the rate at which he produces, which is the derivative of q is negative 9t squared plus 18t plus 12. All right. And you know what? I copied this problem down wrong, and I got to change it because I don't know if the numbers will come out right. But basically what I did wrong is there's not supposed to be a 3 in front of t cubed. It's supposed to be negative t cubed. Sorry about that. So that's just negative t cubed. Okay, so let's do this over. All right. So I've got r of t is equal to the derivative of q of t. I just copied the problem down wrong. Everybody makes mistakes. So it's negative 3t squared plus 18t plus 12. So this is the rate. Let's write that down. That's his rate, or the average worker's rate. All right. So what do we want to know? We want to know what? We want to know when is his rate a maximum? When is his rate a maximum? So that's just finding the derivative of this and determine where the relative maximum is. That's what we're looking for. So if I do r prime of t, that's equal to negative 6t plus 18. So negative 6t plus 18 equals 0. So t is equal to 3. And if you look at this, there's 3, there's 0, and there's 4. Okay, we can't go below 0. We can't go above 4. So basically, we're working within just this region right here. Okay, because we're just looking at the morning shift from 8 to 12. So I've got t equals 1, t equals say 3.5. Okay, so I've got r prime of 1, r prime of 1. If I plug the 1 into here, that's positive, and so that's increasing. And then the 3.5, plug that into there, r prime of 3.5, that is going to be negative, because think about it, 6 times 3 is 18, so 6 times 3.5 is more than 18, so I've got a negative number that's more than 18, so that's negative, so that's decreasing. And so we show that there is a maximum at 3. Okay, that's a maximum there. So we're going to say at what, 11 a.m. is when their rate is most efficient, because that's what it starts at 8, and when t equals 3, it's 11 a.m. because that's 3 hours from 8 o'clock. And so there's your answer. All right. So I hope you enjoyed that video. Go check out my other ones. Give me a like, share, subscribe, comment, and I will see y'all in the next one. Later.